Quantum fields are the invisible threads weaving the fabric of reality. By exploring 30 distinct theories about these fields, you will discover how they connect the smallest particles to the largest structures and why so much remains unknown. This framework revolutionized 20th century physics by merging quantum mechanics with special relativity into a single language. Some of these ideas have already reshaped our understanding of the cosmos, while others await confirmation or refutation. Our journey begins with the simplest and most established formulation. What lies beneath the surface of everything we know? Quantum field theory is the language of modern particle physics. For decades, we thought the universe was built from tiny solid building blocks called particles, electrons, protons, neutrons. But as scientists probed deeper, they discovered that this picture was incomplete. Particles are not the fundamental objects. The fundamental objects are fields. Imagine an invisible ocean of energy that fills all of space and time. This ocean exists everywhere, even in the emptiest vacuum. What we call a particle is simply a localized ripple, an excitation in that ocean. When the field vibrates in a particular way, we detect an electron. When it vibrates differently, we detect a photon. The field itself is the real substance. The particle is just a temporary disturbance. This shift in perspective brings three core principles into focus. First, locality. Every event in a field only affects its immediate surroundings. Nothing jumps across space without passing through the points in between. Second, causality. Cause always comes before effect. No signal travels faster than light, so no effect can outpace its cause. Third, Lorentz invariance. The laws of physics remain the same for all observers moving at constant speed, whether they are standing still or racing through the cosmos. These principles ensure that quantum field theory respects both quantum mechanics and Einstein's theory of special relativity. The success of this framework is staggering. It has predicted the existence of particles like the Higgs boson decades before they were found in experiments. It explains how light and matter interact with extraordinary precision, down to 1 part in a trillion. Every experiment at particle colliders, every calculation in modern high-energy physics rests on quantum field theory. It is the most rigorously tested and confirmed theory we have. Yet quantum field theory is not the final answer. It is the canvas upon which more speculative ideas are painted. Every theory we explore in this list builds upon the foundation that fields are real, that particles are ripples, and that the vacuum is not empty but alive with potential. Understanding this canvas is the first step toward seeing how the universe might be far stranger and more interconnected than we ever imagined. One of the most famous quantum fields is the Higgs field. While other fields like the electromagnetic field give rise to light and forces, the Higgs field plays a unique role. It fills all of space, even the deepest vacuum, and it does something remarkable. It gives mass to the elementary particles. To understand how, we need to look at a concept called spontaneous symmetry breaking. Picture a perfectly round dinner plate balanced on its edge. The plate is symmetric. It could fall in any direction, but once it tips, it chooses one specific direction to rest. The symmetry is broken. In the early universe, just after the Big Bang, all particles were massless. They zipped around at the speed of light, but as the universe cooled, the Higgs field underwent a phase transition, much like water freezing into ice. The field settled into a state with a non-zero value everywhere. This is called a non-zero vacuum expectation value. It means the field is never truly zero. It has a constant, tiny energy that pervades all of space. As particles move through this field, they interact with it and become sluggish. That sluggishness is what we recognize as mass. The more a particle interacts with the Higgs field, the heavier it is. Photons, for example, do not interact at all and remain massless. Electrons interact only a little, giving them a small mass. The top quark interacts a lot and is extremely heavy. This process, the Higgs mechanism, was first proposed in the 1960s. For decades, it remained a brilliant but untested idea. Then, in 2012, scientists at the Large Hadron Collider announced the discovery of the Higgs boson. This particle is a ripple in the Higgs field itself, and its existence confirmed the mechanism. It was a triumph of human curiosity and experimental skill. Yet, like all great discoveries, it opened new questions. The Higgs boson has a mass that seems unnaturally small compared to the enormous energies that should naturally arise from quantum effects. This puzzle is known as the hierarchy problem. Why is the Higgs mass so tiny? Why aren't the forces we see completely overwhelmed by these quantum corrections? These questions point to deeper physics beyond our current understanding. The Higgs field is not alone. There may be other scalar fields hiding in the cosmos, fields that could explain dark energy, cosmic inflation, or even the nature of time itself. The Higgs is just the first, and its discovery has given us a powerful new lens through which to search for the others. Quantum electrodynamics is the most precisely tested theory ever devised. It describes the interaction between light and matter, specifically between electrons and photons. At its heart, QED is the quantum field theory that explains how charged particles exchange packets of light energy to create forces like electricity and magnetism. The theory emerged from the work of physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the 1940s, and it remains one of the crown jewels of modern science. What makes QED extraordinary is its precision. Its predictions have been verified by experiments to an accuracy of 1 part in a trillion. For comparison, that is like measuring the distance from Earth to the Moon and being off by less than the width of a human hair. No other scientific theory comes close to this level of agreement between calculation and observation. To achieve this precision, physicists had to solve a deep problem. When they tried to calculate the behavior of an electron interacting with its own field, the equations produced infinities. These infinite results seemed to make the theory meaningless. But a clever mathematical technique called renormalization rescued QED. Renormalization works by recognizing that some quantities, such as the electron's mass and charge, are not the bare values appearing in the equations. Instead, they are the measured values we see in experiments, which already include the effects of all the quantum fluctuations. By carefully subtracting the infinities and redefining the constants in terms of measurable numbers, the theory produced finite, sensible results. Renormalization is not a trick. It is a systematic way to handle the fact that our equations describe only a limited range of energies and distances. It tells us that the theory is an effective description, valid up to some very high energy scale. Feynman revolutionized the calculation of these processes with simple diagrams that now bear his name. A Feynman diagram represents a specific sequence of particle interactions. For example, imagine 2 electrons approaching each other. In the diagram, they exchange a wavy line representing a photon. This photon is not a real particle that could be detected directly. It is called a virtual particle, a temporary fluctuation that exists only within the interaction. Virtual particles violate the usual energy conservation rule for an extremely short time, thanks to the uncertainty principle. They are the messengers of the force. Without them, the electrons would never know the other is there. QED serves as the prototype for every other gauge theory in physics. Gauge theories are the foundation of our understanding of fundamental forces. The strong nuclear force described by quantum chromodynamics and the weak nuclear force, unified with electromagnetism in the electroweak theory, are direct descendants of QED. The same principles of exchange particles, renormalization, and Feynman diagrams apply, though with added complexity. QED showed that it was possible to write a consistent quantum field theory that matched reality with breathtaking accuracy. Its success gave physicists the confidence to push deeper into the unknown. to ask what other forces might be explained by similar fields and what other particles might be hiding in the quantum foam of empty space. The story of QED is a story of human ingenuity overcoming paradox, and its legacy is woven into every particle collider experiment and every calculation that predicts the behavior of matter at its most fundamental level. The strong nuclear force required its own quantum field theory. This theory is called quantum chromodynamics, or QCD for short. While quantum electrodynamics describes how light and matter interact, QCD describes how quarks and gluons bind together to form protons, neutrons, and all other hadrons. The force they feel is the strongest in nature, holding the nucleus of every atom together against the electromagnetic repulsion of protons. The key to QCD is a property called color charge. Do not think of actual visible color. Think of it as a kind of internal charge that comes in three types, simply named red, green, and blue. Quarks carry one unit of this color charge, and antiquarks carry the opposite color. Gluons, the force carriers, carry a combination of color and anticolor. This is very different from the photon in QED, which has no electric charge. A gluon itself carries color charge, so gluons can interact with each other. This self-interaction makes the strong force behave in strange and dramatic ways. The most striking feature of QCD is confinement. No matter how hard you try, you cannot separate a quark from its companions. If you try to pull two quarks apart, the gluon field between them stretches into a narrow tube or string. The energy stored in this tube increases with distance, like a rubber band being stretched. At some point, the energy becomes so large that it spontaneously creates a new quark and antiquark pair from the vacuum. The original quarks then bind with these new particles, and you end up with two separate hadrons instead of a free quark. This is why quarks never appear in isolation. They are always locked inside composite particles like protons or neutrons. At very short distances, however, something remarkable happens. Quarks behave almost as if they are free. This is called asymptotic freedom. When quarks are extremely close together, the strong force weakens dramatically. This behavior is the opposite of what we see in electromagnetism. It means that inside a proton, quarks can move around nearly independently, but they cannot escape. Asymptotic freedom was discovered in the 1970s and earned the Nobel Prize for Gross, Politzer, and Wilczek. It is the reason we can use perturbation theory to calculate high-energy collisions at particle accelerators. But at low energies where confinement dominates, perturbation theory fails completely. To understand the masses and properties of protons, neutrons, and other hadrons, physicists use a technique called lattice QCD. They divide spacetime into a discrete grid of points like a three-dimensional chessboard. On each point, they place the quark and gluon fields. Then they simulate the quantum behavior using supercomputers. By averaging over millions of configurations, they can compute the masses of hadrons from first principles. These calculations match experimental measurements with remarkable precision. Lattice QCD has shown that the mass of a proton comes mostly from the energy of the gluon field, not from the masses of its constituent quarks. The quarks themselves are lightweight, but the binding energy is enormous. The gluon fields in QCD are incredibly complex. Because gluons carry color charge, the field lines interact with each other, forming flux tubes and even glue balls, which are hypothetical particles made entirely of gluons. These self-interactions create a rich landscape of non-perturbative phenomena that cannot be captured by simple diagrams. The vacuum itself is filled with fluctuating gluon fields that can condense into a kind of glue. This complicated structure makes QCD one of the most challenging theories to solve, but also one of the most fascinating. Without QCD, there would be no atomic nuclei. No stars, no planets, no life. Every stable nucleus in the universe is held together by the strong force described by this theory. Understanding nuclear matter, from the heart of a neutron star to the fusion reactions inside the Sun, depends on our ability to grasp the behavior of quarks and gluons. QCD is not an obscure corner of physics, it is the bedrock of the material world. By the 1960s, physicists had two separate theories for two of nature's forces. Quantum electrodynamics handled electromagnetism with stunning accuracy. A separate theory called the weak interaction explained radioactive decay and processes like beta decay, where a neutron transforms into a proton inside an atomic nucleus. But these two theories looked nothing alike. The weak force had a serious problem. Its force carriers, called the W bosons, had to be massive to explain the very short range of the weak force, but any attempt to include mass in the theory broke the mathematical consistency that made QD work. This was a crisis. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently realized that the key to solving this crisis was unification. They proposed that at very high energies, electromagnetism and the weak force are actually two facets of a single electroweak force. But to make this work, they needed a mechanism for the W bosons to gain mass without ruining the theory. That mechanism was the Higgs field. In the electroweak theory, the Higgs field is essential for breaking the symmetry. Before symmetry breaking, there are four massless force carriers. Three of them become the massive W+, W-, and Z bosons. The fourth remains massless and becomes the photon. This process also gives mass to the quarks and leptons, the particles that make up matter. The theory predicted a new phenomenon called neutral currents. In the weak interaction, there are two types of processes. Charged currents involve the exchange of the electrically charged W bosons, changing the type of particle involved. Neutral currents involve the exchange of the neutral Z boson, where particles interact without changing their identity. In 1973, experiments at CERN in the Gargamel bubble chamber detected neutral currents for the first time. It was a major breakthrough. The theory predicted very specific properties for the Z and W bosons, including their masses. In 1983, CERN's superproton synchrotron was converted into a collider. With a brilliant modification, it produced beams of protons and antiprotons colliding head-on. The energy was high enough to create the W and Z bosons. One after another, the massive particles were detected, and their masses matched the theoretical predictions almost exactly. The discoveries were so significant that the Nobel Prize followed quickly for Carlo Rubbia and Simon van der Meer, the experimental leaders. The electroweak theory was confirmed. This unification showed that two seemingly different forces were actually connected at a deep level. At everyday energies, they look distinct. The electromagnetic force has infinite range, while the weak force is confined to subatomic distances. But at energies around 100 times the mass of a proton, they merge into a single electroweak force. This insight opened the door to something even bigger. If electromagnetism and the weak force could be unified, what about the strong force? Was there a grand unified theory that could bring all three non-gravitational forces together? The electroweak theory gave physicists the blueprint. It showed that the same symmetry-breaking mechanism, the Higgs field, could produce the mass differences we observe. It also suggested that at even higher energies, the strong force might join in. The search for grand unification had begun. The electroweak theory was not just a success in its own right. It was a stepping stone toward a deeper understanding of reality. It taught us that the universe's forces may be unified at the very beginning of time, only to split apart as the cosmos cooled. And it raised the tantalizing possibility that there might be more than one Higgs field, more than one symmetry-breaking event in the early universe. Those ideas would lead us into territory that still challenges the brightest minds today. The electroweak success pointed toward an even bolder ambition. If two forces could merge at high energies, perhaps all three non-gravitational forces could become one. Physicists began constructing grand unified theories, or GUT, that would encompass the strong nuclear force alongside the electroweak force. The simplest version uses a mathematical structure that contains the separate symmetries of the strong, weak, and electromagnetic interactions. In this framework, at energies far beyond what any collider can reach today, the three forces become identical. They are merely different aspects of a single unified field. This idea is extraordinarily beautiful, but it comes with a startling prediction. Protons, which we normally think of as stable forever, would not be eternal. They would occasionally decay into lighter particles like positrons and neutral pions. The predicted lifetime is enormous, around 10 to the 31 years, many orders of magnitude longer than the age of the universe. Yet such decay should happen rarely but measurably. Physicists built enormous detectors filled with thousands of tons of water deep underground to search for these events. They waited and watched for years. So far, no convincing signal of proton decay has been found. This absence puts strong constraints on the simplest grand unified models. But the idea did not die, it evolved. A major obstacle is the hierarchy problem. The Higgs boson has a mass of about 125 giga-electronvolts. The grand unification scale is roughly 10 to the 16 giga-electronvolts. That is a gap of 14 orders of magnitude. In quantum field theory, the Higgs mass receives enormous quantum corrections from virtual particles at the unification scale. Those corrections should push the Higgs mass up to that enormous scale unless some extraordinary cancellation occurs. Without an explanation, this fine-tuning feels unnatural. One of the most popular solutions is supersymmetry. Supersymmetry proposes that every known particle has a heavier partner. For every fermion, there is a boson partner and vice versa. These superpartners contribute opposite sign quantum corrections to the Higgs mass. If the partners are not too heavy, their contributions cancel the dangerous corrections and keep the Higgs mass naturally small. This idea made supersymmetry a central ingredient in many grand unified theories. With supersymmetry, the three forces appear to converge at a single energy scale much more precisely than they do without it. This convergence is tantalizing. It suggests that nature may be using supersymmetry to unify the forces at a high energy. Yet despite decades of searching at the Large Hadron Collider, no superpartners have been found. This has pushed the possible masses of these particles to higher values, making the cancellation less perfect and the theory less elegant. Grand unified theories remain speculative. No direct evidence for them exists, but they provide a compelling framework that connects the low-energy world we observe to the extreme conditions of the early universe. They imply that matter is not eternal, that the three forces are not truly separate, and that the vacuum may hide a deeper symmetry waiting to be uncovered. The search for proton decay continues in new experiments. The search for supersymmetry continues as well. And even if the simplest models are wrong, the idea of grand unification has profoundly shaped how we think about the cosmos. It has pushed us to ask whether all forces are ultimately one, and whether the universe at its birth was a perfectly symmetric fireball of pure unified energy. Supersymmetry doubles the number of fundamental particles in a bold new way. Every fermion, the matter particles like electrons and quarks, gains a boson partner whose name begins with an S. So the electron partners with this electron, the quark with the squark. Every boson, the force carriers like the photon and gluon, gains a fermion partner ending in ino. The photon partners with the photino, the gluon with the gluino. This symmetry between matter and force restores a deep balance in nature. It is not a random addition. It solves a pressing puzzle that emerged from grand unified theories. The Higgs boson receives enormous quantum corrections from virtual particles. Without supersymmetry, these corrections would push the Higgs mass to an absurdly high value. With supersymmetry, each virtual particle's contribution is cancelled by its superpartner because fermions and bosons contribute with opposite signs. If the superpartners are not too heavy, the cancellations keep the Higgs mass naturally low. That is the hierarchy problem solved, but supersymmetry also offers a gift to cosmology. In many versions of the theory, the lightest supersymmetric particle is stable. It does not decay into anything else. This particle, often a neutrino that mixes the photino, xeno, and Higgsino, has the right properties to be dark matter. It is electrically neutral, weakly interacting, and massive. It would clump around galaxies and account for the missing mass that holds them together. Supersymmetry emerged from theoretical beauty, but it also gained support from string theory. The mathematics of superstrings only works consistently if supersymmetry exists in nature. It provides a bridge between our four-dimensional world and the extra dimensions that string theory requires. It is the bedrock upon which the most ambitious unified theories are built. Yet the experimental search has not been kind. The Large Hadron Collider at CERN, with its enormous energy, has looked for signs of squarks, gluinos, and leptons. It has found nothing so far. Each null result pushes the possible masses of these particles higher, making the theory less elegant and the fine-tuning more severe. The window for natural supersymmetry is closing, but the theory does not die, it evolves. Supersymmetry remains one of the leading theoretical extensions of the Standard Model. It solves multiple problems at once, predicts a dark matter candidate, and connects to the deepest ideas about space and time. Even without experimental confirmation, it guides much of the thinking in fundamental physics. The search continues not just at colliders but in underground detectors hunting for the faint signals of dark matter particles. Supersymmetry may yet be discovered, or it may fade into the category of beautiful ideas that nature chose not to use. Either way, it has already reshaped how physicists imagine the universe at its most fundamental level. String theory takes this reshaping even further by replacing point particles with vibrating strings. Every particle that we know, every electron, quark, and neutrino, is not a tiny dot. It is a one-dimensional loop or strand of energy. The way this string vibrates determines what kind of particle we observe. One pattern of vibration produces an electron, a different pattern produces a quark, a third produces a photon. All particles become different notes played on the same fundamental instrument. But string theory does not abandon the ideas we have explored so far. It depends on quantum field theory in a deeply intimate way. As a string moves through spacetime, it sweeps out a surface called the world sheet. This world sheet is two-dimensional, one dimension of space and one of time. The mathematics that describes the dynamics on this world sheet is itself a quantum field theory. It is a two-dimensional field theory that governs how the string vibrates, how it splits and joins with other strings, and how it interacts. The entire machinery of particle physics, the forces, the particles, the symmetries, rests on this foundation. From this perspective, spacetime is not the stage upon which the play unfolds. It is something that emerges from the dynamics of the strings themselves. The four dimensions we experience every day arise as a low-energy approximation of a much richer structure. String theory requires extra dimensions, typically 6 or 7, curled up so tightly that we do not notice them at ordinary scales. The exact shape of these hidden dimensions determines the masses of the particles we see and the strengths of the forces that act on them. Change the shape and you get a different universe. The gauge fields that mediate the fundamental forces also emerge from the behavior of strings. Open strings have two ends, and those ends can be attached to surfaces called D-branes. These D-branes are like membranes floating in the higher dimensional space. The open strings vibrate and stretch along these branes. Their quantum excitations produce exactly the kind of gauge fields that we find in quantum chromodynamics and the electroweak theory. It suggests that the Standard Model particles are not fundamental at all. They are vibrations of strings trapped on a set of branes in a much larger cosmos. The deepest surprise from string theory is a discovery known as the AD-S/CFT correspondence. This duality links a theory of gravity living inside a special type of curved space called anti-de Sitter space to a conformal field theory living on the boundary of that space. The conformal field theory is a quantum field theory with no gravity at all, yet it contains every bit of information about the gravitational physics happening inside the volume. Gravity in the interior is completely equivalent to a quantum field theory on the boundary. The geometry of spacetime is not fundamental. It is a hologram projected from the quantum fields that lie on the edge. Through this correspondence, string theory offers a quantum field theoretic description of gravity. It tells us that the gravitational force, the bending of space and time, can be rewritten in the language of fields and particles. It gives physicists a way to calculate things that were previously impossible, like the entropy of a black hole or the behavior of matter in extremely strong gravity. The AD-S/CFT correspondence is one of the most fertile ideas in modern theoretical physics. It connects string theory directly to the world of quantum fields and opens a window into what lies beyond our current picture of reality. The story of string theory eventually led to an even deeper revelation. There are actually 5 distinct superstring theories, each living in 10 dimensions, and each with its own set of mathematical rules and particles. For a while, physicists wondered which one described our universe. The answer surprised everyone. All 5 are connected by a web of dualities, transformations that map one theory onto another. These dualities suggested that behind the scenes, a single, more fundamental theory was hiding. That theory became known as M-theory. M-theory lives in 11 dimensions, one more than the 10 required by string theory. It does not have strings as its only objects. It also contains membranes, which are 2-dimensional surfaces, and 5 branes, which extend across 5 spatial dimensions. These extended objects interact and transform into one another through the dualities. The low energy limit of M-theory is a quantum field theory called 11-dimensional supergravity. This theory includes a very special field called the 3-form. A 3-form is a mathematical object that can be integrated over a 3-dimensional volume. In 11-dimensional supergravity, this 3-form couples to membranes, just as the electromagnetic field couples to charged particles. It is a source of force and energy, and it plays a crucial role in how the extra dimensions curl up. The existence of multiple vacua in M-theory is both a blessing and a challenge. The shape and size of the extra dimensions are not fixed by the theory itself. They are determined by the values of various fields, including the 3-form. This means there is a vast landscape of possible universes, each with different physical constants and laws. Some of these vacua might resemble our own cosmos. Others would be radically different. The landscape idea has deep implications for quantum field theory. It suggests that what we call the standard model is not unique. It is just one low-energy description among countless others. The fields and particles we observe are the result of a particular choice of vacuum, a specific configuration of the extra dimensions. This perspective shifts the question from why the laws are what they are to why we find ourselves in this particular vacuum. M-theory remains a work in progress. It is not yet a complete or fully defined framework. No one knows the fundamental degrees of freedom, the ultimate building blocks that make up the theory. The equations are too complex to solve directly, but through dualities, it has already revolutionized how physicists think about quantum fields. The web of connections shows that seemingly different field theories are actually the same theory expressed in different languages. It has given us tools to calculate properties of strongly interacting systems that were once impossible, and it has opened up a new way of thinking about spacetime itself as something that emerges from the interactions of more primitive objects. The search for the full formulation of M-theory continues, and with it, the hope that one day we will hold the final unified picture in our hands. string theory is not the only approach to quantizing gravity. In fact, it has a rival that starts from a completely different place. Loop quantum gravity does not ask for extra dimensions, higher symmetries, or strings. It takes general relativity as it stands and applies the rules of quantum mechanics directly to the geometry of spacetime itself. The result is a quantum field theory where spacetime is no longer a smooth background. It becomes a granular, discrete fabric made of tiny loops. The central idea of loop quantum gravity is that space is not continuous. At the Planck scale, about a billionth of a billionth of a billionth of a meter, the smooth canvas of the universe breaks into individual units. These units are described by mathematical objects called spin networks. A spin network is a graph of nodes connected by links. Each node represents a quantum of volume, and each link represents a quantum of area. The network encodes the geometry of space at the most fundamental level. The area of a surface and the volume of a region cannot take any value. They come in discrete packets like the energy levels of an atom. This quantization emerges naturally from the equations. It is not put in by hand. To see how this works, physicists start with Einstein's theory of general relativity and rewrite it in the language of connections and triads. This is called the Ashtekar variables, named after the physicist Abhay Ashtekar. The equations become similar to those of a gauge field theory, like the one that describes the strong nuclear force. Then they perform a quantization procedure that respects the symmetries of the theory without ever treating gravity as a small perturbation. That is why it is called non-perturbative. Loop quantum gravity does not assume that gravity is weak. It handles the full nonlinearity of curved spacetime from the beginning. This approach leads to a striking picture. At the Planck scale, space is not empty. It is a seething foam of spin networks with quantum states that constantly rearrange. Time also loses its familiar continuous flow. Instead, it emerges from the ordering of events in the network. Some researchers interpret this as a hint that time itself is not fundamental, but arises from the dynamics of the quantum geometry. How does loop quantum gravity compare to string theory? String theory tries to unify all forces and matter by introducing extra dimensions and supersymmetry. It is perturbative, meaning it often treats interactions as small corrections to a simpler theory. Loop quantum gravity, in contrast, stays within 4 dimensions and focuses purely on gravity. It does not require supersymmetry or extra hidden dimensions. It offers a direct quantization of the gravitational field as a quantum field in its own right. The two frameworks address different aspects of the problem. String theory aims for a grand unification of all forces. Loop quantum gravity aims to understand what spacetime really is at the deepest level. One of the greatest successes of loop quantum gravity is its explanation of black hole entropy. Black holes are predicted to have a temperature and an entropy, a measure of their hidden information. The famous Bekenstein-Hawking formula says that this entropy is proportional to the area of the event horizon. Loop quantum gravity derives this result by counting the number of ways to arrange the spin network states on the horizon. The calculation gives exactly the right coefficient. It matches the prediction from thermodynamics without any extra assumptions. This is powerful evidence that the quantum geometry picture is on the right track. Another major achievement is the resolution of the Big Bang singularity. In classical general relativity, the universe began at a point of infinite density and curvature. Loop quantum gravity replaces that singularity with a big bounce. Instead of collapsing into nothing, the universe contracts, reaches a minimum volume where quantum effects become strong, and then rebounds into a new expanding phase. The same equations that quantize space also prevent the singularity. Time extends backwards beyond the bounce, opening a window into what might have existed before our current cosmos. This idea is testable in principle. The bounce could leave imprints on the cosmic microwave background radiation that future telescopes might detect. Loop quantum gravity does not yet have the same experimental support as quantum electrodynamics or the Standard Model. It remains a work in progress, with many open questions about how to recover the smooth spacetime we experience and how to incorporate matter fields. But it offers a coherent and compelling alternative quantum field theory for gravity. It treats spacetime as a quantum object without needing extra dimensions or new particles. It predicts that space is made of tiny discrete atoms of geometry, and it gives concrete, calculable results for black holes and the early universe. In the ongoing search for a theory of quantum gravity, loop quantum gravity stands as a bold and self-consistent vision, one that keeps the beauty of general relativity intact while embracing the granular nature of the quantum world. Gravity does not have to be quantized to feel its influence on quantum fields. In fact, one of the most successful bridges between Einstein's general relativity and quantum theory is a framework that treats gravity as a classical, curved backdrop while allowing the fields themselves to obey quantum rules. This is quantum field theory in curved spacetime, and it has revealed phenomena that are nothing short of astonishing. The central idea is simple. Instead of quantizing the gravitational field, we take a fixed spacetime geometry, such as the expanding universe or the region around a black hole, and we place quantum fields upon it. The curvature of spacetime changes the equations these fields obey, and the results can be dramatic. One of the most famous predictions is particle creation in an expanding universe. During the early moments of cosmic inflation, the fabric of space stretched at an incredible rate. Quantum fluctuations in fields like the inflaton were stretched to macroscopic scales, imprinting the seeds of all cosmic structure we see today. But the effect is not limited to that one field. In any expanding spacetime, pairs of particles can be created out of the vacuum. The energy to create them comes from the gravitational field itself, drawn from the expansion. This production of particles is not a theorist's fantasy. It has a real, testable consequence. The cosmic microwave background radiation, the leftover glow from the Big Bang, shows the imprints of these quantum fluctuations. Another breathtaking example comes from black holes. Stephen Hawking, in the 1970s, applied quantum field theory to the region near a black hole's event horizon. He discovered that black holes are not completely black. They emit a faint, steady glow of radiation, now called Hawking radiation. The mechanism is deeply linked to the curved spacetime near the horizon. Virtual particle pairs, which constantly pop in and out of existence in empty space, get torn apart by the intense gravity. One particle falls into the black hole, the other escapes to infinity. To a distant observer, the escaping particle looks like real radiation. The black hole loses a tiny amount of mass with each escaping particle, slowly evaporating over enormous timescales. This discovery connected gravity, quantum mechanics, and thermodynamics in a way that no one had anticipated. It also raised the famous information paradox about what happens to the information carried by matter that falls into a black hole. There is an even more peculiar effect that does not require black holes or cosmic expansion at all. It is called the Unruh effect, named after the physicist Bill Unruh, who predicted it in 1976. Imagine an observer who accelerates through empty space at a constant rate. According to the rules of quantum field theory, that observer will see a warm bath of particles, a thermal glow, where an inertial observer sees nothing. The accelerating observer's horizon, similar to a black hole's event horizon, separates what they can and cannot detect. The very act of acceleration changes what counts as a particle. The vacuum is not a fixed concept. It depends on the motion of the observer. This means that the number of particles is not an absolute quantity. It is relative to how you move through spacetime. These semi-classical results, where gravity is classical and fields are quantum, are not just intellectual curiosities. They provide the strongest evidence we have that quantum field theory and general relativity can coexist, at least in regimes where gravity is not too strong. They also give us clues about what a full theory of quantum gravity must look like. For example, Hawking radiation implies that black holes have a temperature, which in turn suggests that they have a microscopic structure, a statistical counting of states that loop quantum gravity and string theory both try to calculate. The Unruh effect hints at a deep connection between acceleration, temperature, and the very definition of a particle. It tells us that the vacuum is far from empty. It is a dynamic, observer-dependent state. By studying quantum fields on curved backgrounds, we learn that spacetime is not just a stage where particles perform. It actively participates, creating and destroying particles, shaping their behavior, and tying the quantum world to the geometry of the cosmos. This approach bridges two great pillars of modern physics without requiring a complete quantum theory of gravity. It is a stepping stone, a guide, and a source of deep puzzles that still challenge us. The next step beyond this semi-classical approximation is to treat gravity itself as a quantum field, to find a unified framework where spacetime and particles emerge from the same fundamental principles. We have already seen two ambitious attempts, string theory and loop quantum gravity. Now we must ask what happens when we try to quantize the gravitational field directly, not as a fixed background but as a dynamical quantum entity. That journey takes us deeper into the unknown. Inflation is the most dramatic example of a quantum field shaping the entire cosmos. The inflaton field is a hypothetical scalar field that existed in the first fraction of a second after the Big Bang. It drove a period of exponential expansion so rapid that the universe grew by a factor of at least 10 to the 26 in an unimaginably short time. This single burst solved several profound puzzles. It explained why the cosmic microwave background is so uniform across the sky, because regions that are now far apart were once in causal contact before inflation separated them. It also explained why the universe appears geometrically flat, because the enormous expansion stretched any initial curvature to near zero. But the most remarkable consequence of inflation is that it provided the seeds for all cosmic structure. During inflation, quantum fluctuations in the inflaton field were stretched to macroscopic scales by the rapid expansion. These tiny variations in the field's energy density became ripples in the fabric of spacetime itself. After inflation ended, those ripples imprinted themselves on the distribution of matter, eventually growing into the galaxies, stars, and planets we observe today. The precise pattern of these fluctuations has been measured by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck mission. The data match the predictions of inflation with stunning accuracy, especially the nearly scale invariant spectrum of fluctuations and the slight tilt that favors larger structures. There are many models of the inflaton field, each proposing a different shape for its potential energy curve. Chaotic inflation assumes a simple quadratic or quartic potential, allowing inflation to occur naturally for a wide range of initial conditions. Natural inflation arises from a periodic potential generated by a symmetry-breaking mechanism, similar to the Higgs field but at a much higher energy scale. Starobinsky inflation, one of the earliest models, uses a correction to Einstein's gravity that effectively mimics a scalar field. This model fits the observational data extremely well and remains a leading candidate. Despite these successes, the fundamental nature of the inflaton remains unknown. No direct detection of the inflaton particle has ever been made. We do not know whether it is a new fundamental field or an emergent effect of a deeper theory. Some grand unified models connect the inflaton to the Higgs field, while others embed it within string theory or supergravity. The energy scale of inflation is far beyond what any collider could ever reach. Yet its effects are written across the sky. The cosmic microwave background carries the signature of quantum fields operating at energies near the unification scale. Inflation is not merely a hypothesis, it is the leading paradigm for the early universe, supported by a web of consistent observations. The question of what the inflaton actually is remains one of the deepest open problems in cosmology. It ties together quantum field theory, general relativity, and the conditions at the birth of the cosmos, and it hints that the vacuum of the early universe was not empty at all, but filled with a field that powered the greatest expansion event in history. Deep inside the strong nuclear force, a subtle puzzle has challenged physicists for decades. The theory of quantum chromodynamics includes a term that would violate a fundamental symmetry called CP, which relates particles to their mirror images. Yet every experiment shows that this violation is essentially zero. The strong force behaves as if the offending term simply does not exist. This is the strong CP problem, and it is one of the most finely tuned mysteries in all of physics. The most elegant solution came from Roberto Pexi and Helen Quinn in 1977. They proposed a new symmetry that, when broken spontaneously, forces the troublesome term to vanish. The breaking of this symmetry produces a new particle, a ripple in the associated field, which they named the axion. The axion is a special kind of particle called a pseudo-Nambu-Goldstone boson. It is extremely light, perhaps a millionth of the mass of an electron, and it interacts only incredibly weakly with ordinary matter. Its very existence would erase the strong CP violation without any fine-tuning. But the axion does more than solve a particle physics puzzle. It also emerges as a compelling candidate for dark matter. In the early universe, the axion field would have started oscillating when the universe cooled below a certain temperature. Those oscillations behave like a cold fluid of particles, clustering under gravity and providing the missing mass that holds galaxies together. The axion weighs so little and interacts so weakly that it would never have been detected in any particle collider. Instead, physicists have devised ingenious experiments to catch it. Haloscopes are devices that use a strong magnetic field to convert axions from the galactic dark matter halo into a faint microwave signal. Helioscopes point at the Sun, looking for axions that might be produced in the solar core, and then convert into X-rays in a magnetic field. So far, no experiment has found a convincing signal, but the search continues with ever greater sensitivity. The axion idea has taken on a new life in string theory, where many such light fields naturally arise from the compactification of extra dimensions. Some cosmologists now believe that the universe may be filled not with one axion but with a whole family of axion-like particles, each with its own tiny mass. Together, they could solve multiple puzzles at once, explaining dark matter, the strange properties of dark energy, and even the observed isotropy of the cosmos. The axion remains one of the most promising and testable ideas beyond the standard model, a quiet field that may yet reveal itself in the hum of a laboratory magnet or the glow of a distant star. The same quantum fields that birth particles and shape the early universe also pose one of the deepest riddles in modern physics. Dark energy is the name given to the mysterious force that is causing the expansion of the universe to accelerate. The simplest explanation comes directly from quantum field theory, the energy of empty space itself. According to our best calculations, the quantum vacuum should be seething with energy, a constant background hum from all the virtual particles popping in and out of existence. Every field, from the electromagnetic to the Higgs, contributes to this vacuum energy. When physicists add up these contributions, the total is astronomically large, something like 10 to the 120 times larger than the energy density we actually observe driving cosmic expansion. That is a discrepancy of 120 orders of magnitude, the worst theoretical prediction in the history of science. If this vacuum energy were as large as our equations suggest, the universe would have blown itself apart in a fraction of a second after the Big Bang. Clearly, something is cancelling nearly all of it, or our understanding of the vacuum is fundamentally incomplete. This is the cosmological constant problem, and it has haunted physicists for decades. The cosmological constant is the term Einstein originally added to his equations of general relativity to keep the universe static, then removed when the expansion was discovered. Later, it was resurrected as the simplest model for dark energy. It represents a constant, unchanging energy density that fills all of space uniformly. It does not dilute as the universe expands, unlike matter or radiation. The observational evidence from distant supernova, the cosmic microwave background, and the large-scale structure of galaxies all points to a very small but non-zero value for this constant. But why is it so small? Some physicists argue that a yet unknown symmetry may force the total vacuum energy to vanish almost exactly, leaving only a tiny residual that we call dark energy. Others invoke the anthropic principle, suggesting that only in universes with a very small cosmological constant can intelligent observers arise. But the most active alternative to a constant is the idea of quintessence. Quintessence proposes that dark energy is not a fixed property of spacetime but a dynamical scalar field, much like the inflation that drove cosmic inflation. This field, often called the quintessence field, has its own potential energy that slowly changes over time. As the universe expands, the field rolls down its potential and its energy density gradually evolves. This could explain why the dark energy we see today is so small, because the field has been rolling for billions of years and has not yet reached its true minimum. Quintessence also allows for subtle variations in the expansion rate over cosmic history, which future observatories might detect. The key point is that both the cosmological constant and quintessence are intimately tied to quantum fields. The cosmological constant is the vacuum expectation value of those fields, and quintessence is a new field itself. We cannot understand dark energy without quantum field theory, and yet quantum field theory seems to give an answer that is wildly wrong. This tension drives much of the current research in theoretical physics. It suggests that our current framework is missing something essential, perhaps a deeper symmetry, a connection to quantum gravity, or a completely new understanding of what the vacuum really is. The answer may come from a combination of observations and theoretical breakthroughs, or it may remain one of those questions that reshapes our entire conception of reality. Every time we think of empty space, we imagine a perfect void, a silent nothingness. But quantum field theory insists that even the most pristine vacuum is alive with activity. Particles and their antiparticles flicker into existence from pure energy, live for an unimaginably brief instant, and then annihilate each other back into nothing. This ceaseless dance is not a flaw in the theory. It is a direct consequence of the uncertainty principle, which allows temporary violations of energy conservation as long as they last a very short time. The shorter the lifetime, the larger the energy that can be borrowed. The vacuum is not empty, it is a restless sea of virtual particles. These fluctuations are not just philosophical curiosities. They have measurable, observable effects that have been confirmed in laboratories around the world. One of the most famous is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed extremely close together in a vacuum would experience a tiny attractive force. The reason lies in the quantum vacuum itself. Between the plates, only certain wavelengths of virtual particles can exist, those that fit neatly into the gap. Outside the plates, all wavelengths are allowed. This imbalance creates a net pressure that pushes the plates together. The force is minuscule, barely detectable, but it has been measured repeatedly and matches the theoretical prediction. It is a direct physical manifestation of the quantum vacuum. Another striking consequence is the Lamb shift, discovered by Willis Lamb in 1947. In the hydrogen atom, two energy levels that should be identical according to the Dirac equation turn out to be slightly different. The reason again involves virtual particles. The electron orbiting the nucleus is constantly interacting with the sea of virtual photons that pop in and out of existence. These brief interactions nudge the electron's energy slightly, shifting the levels apart. The Lamb shift was one of the first clues that the quantum vacuum is real, and it helped spark the development of modern quantum electrodynamics. Spontaneous emission of light from an excited atom provides a third example. Without the quantum vacuum, an excited atom would never release its energy. It would remain in that state forever. But the vacuum fluctuations act as a tiny perturbation, a gentle nudge that stimulates the atom to emit a photon and drop to a lower level. The emitted light is not caused by any external field. It is caused by the vacuum itself. The rate of spontaneous emission can be calculated and matches experiments beautifully. All of these phenomena trace back to a single concept, zero-point energy. Even at absolute zero temperature, when all thermal motion has stopped, the quantum fields still possess a minimum amount of energy. This is the energy of the vacuum itself. The Higgs field has its non-zero vacuum expectation value. Each field, from the electromagnetic to the gluon to the electron, contributes its own zero-point energy. When physicists add up all these contributions from all known fields, the number is enormous, so large that it should warp the entire universe with its gravitational pull. This is exactly the cosmological constant problem we discussed earlier. The vacuum fluctuations predicted by quantum field theory give a value for dark energy that is far larger than what we observe. The discrepancy is a profound mystery. Something must be cancelling almost all of this zero-point energy, perhaps a symmetry we have not yet discovered, or perhaps our understanding of gravity must change at these scales. But the vacuum fluctuations themselves are not in doubt. They have been measured in the Casimir effect, the Lamb shift, and spontaneous emission. They are as real as the force that holds an atom together. The quantum vacuum is not an empty stage. It is the most active, energetic, and puzzling entity in all of physics, and its influence reaches from the smallest atomic shifts to the largest cosmic expansion. The Casimir effect proves that empty space can push things together with a measurable force. Two uncharged metal plates placed mere micrometers apart in a vacuum feel an invisible attraction. The reason lies entirely in the quantum fields that fill the void. Outside the plates, all possible wavelengths of virtual particles exist, a full orchestra of fluctuations. Inside the narrow gap, only those wavelengths that fit comfortably between the plates are allowed. The longer wavelengths are cut off like a low note that cannot resonate in a tiny room. This difference creates an imbalance. The pressure of virtual particles outside exceeds the pressure inside, and the plates are gently pushed toward each other. The force is tiny, barely 1/10,000th of a gram for a plate the size of a coin, but it is real. It has been measured in laboratories since the late 1990s, first by Steve Lamoureux at the University of Washington, and later with far greater precision by other groups. The experimental results match the quantum field theory predictions to within a few percent. The Casimir effect is not a fringe phenomenon. It is a direct macroscopic consequence of the vacuum structure. It tells us that the vacuum is not a passive background. It is an active medium with physical properties that can be manipulated by changing the boundaries. This discovery has practical implications as well. In the world of nanotechnology, where machines are built on the scale of atoms, the Casimir force becomes a dominant player. It can cause tiny moving parts to stick together, a problem called stiction that engineers must overcome. It can also be harnessed to create novel sensors and actuators that respond to changes in geometry. The force depends on the shape and material of the objects, opening the door to designing surfaces that either attract or repel through careful engineering. Deeper still, the Casimir effect connects to the enigma of vacuum energy. The same zero-point fluctuations that push plates together account for a huge chunk of the energy budget of the universe, at least according to our equations. But the observed cosmological constant is vastly smaller. Something must be cancelling most of that energy, and the Casimir effect provides a controlled laboratory environment to study how boundary conditions influence the vacuum. It is a window into the nature of empty space, a reminder that nothingness is far richer than we ever imagined. If quantum fields can exert forces on metal plates, what other hidden powers might they possess, waiting for the right experiment to reveal them? Acceleration changes what you see in the quantum vacuum. If you sit still in empty space, you see nothing but perfect stillness. But if you start moving faster and faster, constantly gaining speed, the vacuum itself begins to glow. This is the Unruh effect, named after the physicist Bill Unruh, who predicted it in 1976. It is one of the most startling consequences of combining quantum field theory with the geometry of accelerated motion. The prediction is simple to state. An observer who accelerates at a constant rate through the Minkowski vacuum, the standard empty space of special relativity, will detect a warm bath of particles. They will feel a thermal glow, a temperature that rises with the strength of the acceleration. Meanwhile, a second observer who is not accelerating, who simply drifts through the same region, sees absolutely nothing. The vacuum is perfectly empty for them. This means that the very notion of a particle is not absolute. It depends on how you move. The vacuum is observer-dependent. What one person calls empty space, another calls a warm gas. This idea is deeply tied to the equivalence principle, the cornerstone of Einstein's general relativity. The equivalence principle states that acceleration is indistinguishable from gravity. If you are inside a closed box that is accelerating through space, you cannot tell the difference between that acceleration and being at rest on the surface of a massive planet. Everything falls to the floor the same way. Unruh realized that if acceleration produces a thermal bath of particles, then gravity itself must do the same. The same logic that gives an accelerating observer a warm glow should also apply near a black hole. The intense gravity near the event horizon is equivalent to a constant acceleration, and thus black holes should emit particles. This is precisely the Hawking radiation we discussed earlier. The Unruh effect and Hawking radiation are two sides of the same coin, both arising from the interplay between quantum fields and the structure of spacetime as seen by different observers. The mechanism behind the Unruh effect is subtle. Virtual particle pairs pop in and out of existence everywhere, even in the vacuum. Normally, they annihilate each other so quickly that they never become real. But for an accelerating observer, the horizon that separates what they can and cannot detect changes the fate of these pairs. One particle can fall behind the horizon while the other escapes, becoming a real detectable particle. The accelerating observer sees a steady stream of these particles, a thermal glow with a temperature proportional to the acceleration. The formula is simple. The temperature equals the acceleration times a constant divided by the speed of light squared times 2 pi. For a human accelerating at a few g's, the temperature is so small that it is utterly undetectable. To reach a temperature of just 1 Kelvin, you would need an acceleration of about 10 to the 20 meters per second squared, far beyond anything we can achieve in a laboratory. This enormous difficulty explains why the Unruh effect has never been directly observed. The required accelerations are billions of times larger than those produced by the strongest particle accelerators. But that does not mean the effect is untestable in principle. Physicists have proposed clever experiments using intense laser fields or ultra-cold atoms to mimic the conditions needed. Some researchers are designing tabletop setups where rapid oscillations of a trapped ion could produce an analog of Unruh radiation. Others look for signatures in high-energy physics, perhaps in the radiation emitted by particles moving through strong electromagnetic fields. The theoretical significance of the Unruh effect is immense. It tells us that the vacuum is not a fixed universal state. It is a concept that depends on the motion of the observer. This forces us to rethink what we mean by empty space. If the particle content of the vacuum changes with acceleration, then perhaps the very fabric of spacetime is not as absolute as we once thought. The Unruh effect is a bridge between quantum field theory and the geometry of motion. It hints that a full theory of quantum gravity will require us to abandon the idea of a single objective vacuum. Instead, we will need a description that accounts for all possible motions, all possible observers, simultaneously. It also reinforces the deep connection between thermodynamics, gravity, and quantum mechanics. The temperature felt by an accelerating observer is not a random phenomenon. It follows a kind of law that connects acceleration with heat, a thread that runs through black hole physics, the early universe, and the very nature of information. The Unruh effect has not been proven in a laboratory, but it is mathematically rigorous within the framework of quantum field theory. It is a prediction that we trust because it emerges from the same equations that correctly describe the Casimir effect, the Lamb shift, and Hawking radiation. If any part of that framework is wrong, the Unruh effect would be wrong too, and so far every test of quantum field theory has passed with flying colors. The effect remains one of the most profound and least understood windows into the nature of reality. It tells us that the vacuum is not empty. It is a living, breathing entity that responds to how you move through it. And if a simple change in motion can reveal a hidden warmth in nothingness, what other secrets might the quantum vacuum be keeping from us? A black hole is not eternal. It slowly fades away, particle by particle. This astonishing idea came from Stephen Hawking in 1974, and it forever changed how we think about the relationship between quantum fields and gravity. The mechanism is rooted directly in the behavior of the quantum vacuum near a black hole's event horizon. Virtual particle pairs constantly flicker into existence everywhere, even in the emptiest space. Normally, they annihilate each other so quickly that they leave no trace, but near the event horizon, something different happens. The black hole's gravity is so intense that it distorts the very structure of the quantum fields. One member of a virtual pair can fall across the horizon, disappearing into the black hole forever. The other, now stranded without its partner, has no choice but to become a real particle. It escapes to infinity, carrying away a tiny amount of energy. To a distant observer, this escaping particle looks like a faint glow, a steady emission of radiation that we now call Hawking radiation. The mathematics behind this process involves a subtle transformation called a Bogoliubov transformation. In simple terms, the gravitational field of the black hole mixes the positive and negative frequency modes of the quantum fields. What appears as a pure vacuum state to a freely falling observer near the horizon looks like a sea of particles to an observer far away. The horizon acts as a kind of boundary that redefines what empty space means. The result is a thermal spectrum, a perfect blackbody radiation with a temperature inversely proportional to the black hole's mass. The smaller the black hole, the hotter it burns. A black hole with the mass of our Sun would have a temperature of only a few millionths of a degree above absolute zero, far too cold to detect, but a microscopic black hole would glow intensely, evaporating in a flash. This radiation carries energy away from the black hole, causing it to lose mass. Over enormous timescales, a black hole can completely evaporate, shrinking until it vanishes. The implications are profound. Black holes are not cosmic vacuum cleaners that swallow everything and never give back. They slowly leak particle by particle until nothing remains. But this evaporation raises a deep problem that has haunted physicists for decades. According to quantum mechanics, information can never be destroyed. If you throw a book into a black hole, the book's information should be encoded in the black hole state. When the black hole evaporates, the Hawking radiation is purely thermal, carrying no information about what fell in. This seems to violate a fundamental principle of quantum theory. This is the information paradox. For years, Hawking himself argued that information was lost, that black holes were a place where quantum mechanics broke down. But later, developments in string theory and the holographic principle suggested otherwise. The AD/CFT correspondence we discussed earlier provided a concrete example where black hole evaporation is unitary, meaning information is preserved. The debate continues, and resolving the paradox is considered one of the most important challenges in theoretical physics. It forces us to confront the nature of spacetime, the meaning of information, and the ultimate fate of anything that crosses a horizon. Hawking radiation is the closest link we have between quantum field theory and black hole thermodynamics. It connects the temperature of a black hole to its surface area, entropy, and the laws of thermodynamics. It is a prediction that has never been directly observed because the radiation from astrophysical black holes is far too faint. But its theoretical foundation is solid, grounded in the same quantum field theory that gave us the Casimir effect and the Unruh effect. It tells us that even the most massive, seemingly permanent objects in the universe are not eternal. They are quantum objects subject to the same restless fluctuations that fill every patch of empty space. And the mystery of what happens to the information they swallow may hold the key to uniting quantum mechanics with the geometry of spacetime itself. The information paradox has become one of the most intense battlegrounds in modern physics. At its core, the problem is simple yet devastating. When a black hole evaporates through Hawking radiation, the particles it emits carry no trace of what fell in. A book, a star, or a simple particle all are reduced to pure thermal glow. Quantum mechanics insists that information can never be erased. The universe keeps a perfect record of every interaction. But black hole evaporation seems to break that rule. If information is lost, then the fundamental laws of physics are incomplete. Something must give. Over the decades, physicists have proposed several dramatic resolutions. One of the earliest ideas is black hole complementarity, first suggested by Leonard Susskind and others. This view holds that no single observer can ever see the whole picture. An astronaut who falls into the black hole experiences a normal crossing of the horizon, while a distant observer sees the astronaut smeared across the horizon and then radiated away. Both descriptions are valid, but they cannot be compared directly because no signal can travel between them. Information is preserved, but it appears in two incompatible ways depending on your perspective. This idea was elegant, but it raised a new puzzle called the firewall paradox. If complementarity holds, then the horizon of an old evaporating black hole should be a region of intense high-energy particles, a firewall that would burn any infalling observer. That seems to violate the equivalence principle, which says that free fall through a horizon should feel like ordinary empty space. In recent years, a more radical solution has emerged from the interplay of quantum field theory and holography. It is called the island formula, and it comes from the AD/CFT correspondence we discussed earlier. The idea is that the information swallowed by a black hole is not lost. Instead, it is encoded in a region of spacetime called an island, which lies inside the black hole but is also connected to the outside through quantum entanglement. The island is not a physical place you can visit. It is a mathematical region that must be included in the calculation of the black hole's entropy. When physicists apply this new formula, they find that the total entropy of the Hawking radiation follows a curve that rises and then falls, exactly as it would if information were being released over time. The paradox dissolves. The island formula has been tested in simplified models of quantum gravity, and it works. It shows that information is preserved not because of any single clever trick, but because the geometry of spacetime itself is woven from quantum fields. The horizon is not a simple boundary. It is a subtle quantum object that connects the inside and outside in ways our classical intuition never predicted. The information paradox is far from settled, but it has already pushed theoretical physics to new heights, forcing us to rethink the nature of spacetime, the meaning of measurement, and the ultimate fate of anything that crosses a horizon. The search for a full resolution is one of the driving forces behind quantum gravity research today, and it may hold the key to the final theory that unites all forces and all fields. The renormalization group reveals that our theories are only approximations of a deeper reality. It is a way of asking what the universe looks like when viewed through different lenses, from the scale of atoms to the scale of galaxies. Every quantum field theory is built to describe nature at a particular energy range. At low energies, we see atoms and molecules. At high energies, we see quarks and gluons. The renormalization group is the mathematical framework that connects these different descriptions. It shows how the laws of physics change as we zoom in or out. Imagine looking at a photograph from very far away. You see a blur of colors and shapes. As you move closer, the blur resolves into individual trees, then leaves, then cells. Each level of magnification reveals a new structure, but the rules that govern that level are different from the ones above or below. The renormalization group formalizes this intuition. It tells us that the parameters of a theory, such as the strength of a force or the mass of a particle, are not fixed constants. They vary with the energy scale at which we probe them. This variation is called the running of the coupling constants. For example, the electromagnetic force becomes slightly stronger at higher energies, while the strong nuclear force becomes weaker. These changes are not random. They follow precise equations known as beta functions, which describe how the coupling constants flow as we move from one energy scale to another. The flow can have fixed points, special energies where the couplings stop changing. A fixed point can be ultraviolet at very high energies or infrared at very low energies. At a fixed point, the theory becomes scale invariant, meaning it looks the same at all magnifications. This is a rare and beautiful property. Conformal field theories, which appear in many areas of physics, are exactly such scale invariant theories. They are the fixed points of the renormalization group flow. The modern understanding of this subject was pioneered by the physicist Kenneth Wilson in the 1970s. Wilson realized that the infinities we encounter in quantum field theory are not a sign of failure. They are a message that our theory is only valid up to a certain energy scale. Beyond that scale, new degrees of freedom appear and the old description breaks down. The process of renormalization is simply a way of hiding what we do not know about the very high energy world. In the Wilsonian approach, we start with a theory defined at some high energy cutoff. This cutoff represents the limit of our knowledge. Then we integrate out the high energy modes, averaging over all the rapid fluctuations we cannot see directly. The result is a new theory at a lower energy scale, with new effective couplings that encode the influence of the hidden high-energy physics. This procedure can be repeated step by step, generating a flow of theories down to the energies we can measure. The key insight is that many different high-energy theories can lead to the same low-energy behavior. This is called universality. The details of the microscopic world are washed out as we move to larger scales, leaving only a few essential parameters. This explains why we can describe the world so well with quantum field theory, even though we do not know the ultimate theory of everything. The renormalization group is a tool of immense power. In particle physics, it explains why the strong force becomes weak at high energies, a phenomenon called asymptotic freedom. In condensed matter physics, it explains phase transitions, such as the point where water turns into steam, by showing how the behavior of countless atoms can be captured by a single set of critical exponents. It even appears in statistical mechanics, biology, and network theory. The renormalization group tells us that all quantum field theories are effective. They are not final, they are useful descriptions tailored to a particular range of scales. This does not make them less valuable, it makes them more honest. The Standard Model itself is almost certainly an effective field theory, valid up to some very high energy where new particles or new forces appear. The quest to find those new degrees of freedom, to probe the next layer of reality, is what drives experimental physics forward. And the renormalization group provides the map for that journey, charting how the laws of nature change as we venture into the unknown. It is the cornerstone of modern theoretical physics, a quiet revolution that reshaped how we think about the very meaning of a law of nature. What if space itself had a built-in fuzziness at the smallest scales? That is the radical proposal of non-commutative quantum field theory. In our everyday experience, the coordinates of space and time are perfectly independent. You can measure where something is along the x-axis without affecting its position along the y-axis. The order in which you make those measurements does not matter. But at the Planck scale, near the limits of our current understanding, this familiar property might break down. The coordinates themselves could become non-commutative, meaning that the act of measuring one coordinate disturbs the other in a fundamental way, much like the uncertainty principle does for momentum and position. This idea is not invented from pure fantasy. It emerges naturally from string theory and from attempts to quantize gravity. In string theory, strings have a finite size, about the Planck length. They cannot be squeezed into a point, so the very notion of a point-like event becomes ambiguous. Spacetime seems to acquire a granular structure, one where the geometry is not smooth but fuzzy. Mathematically, the way to capture this fuzziness is to replace the ordinary multiplication of coordinates with a new deformed multiplication that does not commute. This is a direct extension of the same thinking that gave us quantum mechanics. When two observables do not commute, they cannot be measured simultaneously with perfect accuracy. Here, the observables are the coordinates of space and time themselves. The implications are profound. In a non-commutative spacetime, the rules of quantum field theory must be rewritten. Fields become non-commuting objects, and their interactions become sensitive to the order in which we consider them. One immediate consequence is a violation of locality, the principle that an event can only affect its immediate surroundings. In a non-commutative world, a field at one point can instantly feel a field at a distant point because the very definition of distance becomes smeared. This challenges the idea of causality that we rely on in ordinary quantum field theory. Cause and effect can become blurred, and particles can seem to communicate faster than light, though only over the tiny Planck scale. Another striking effect is called UV/IR mixing. In ordinary quantum field theory, high-energy physics and low-energy physics are separated by the renormalization group. High-energy details are washed out at low energies, but in non-commutative theories, high-energy processes can leave a distinct signature at low energies. The ultraviolet and infrared become entangled. This means that even at accessible energies, we might see hints of Planck-scale physics, a rare and exciting possibility for experimental tests. There could be tiny corrections to the way particles scatter, small shifts in the energy levels of atoms, or subtle modifications to the speed of light for different wavelengths. Astronomers have looked for such dispersion in gamma-ray bursts, cosmic flashes that travel billions of light years. If spacetime had a non-commutative structure, high-energy photons might travel at slightly different speeds than low-energy ones. So far, no such effect has been seen, but the limits are tightening. Non-commutative quantum field theory is not a complete theory of quantum gravity. It is a toy model, a laboratory for exploring what happens when spacetime loses its familiar smoothness. It raises more questions than it answers, but those questions are invaluable. How do we preserve causality in a non-commutative world? Can we build a consistent theory that respects all the symmetries of nature And most importantly, can we ever detect the fuzziness of space in a laboratory? The answers are not yet clear, but the journey itself reveals how deeply quantum fields are woven into the fabric of space-time. They are not just particles and forces. They are threads that, when pulled, begin to unravel the very geometry of the universe. Quantum fields hide patterns that ordinary calculations cannot see. These patterns emerge from the shape of the fields themselves, from the way they twist and knot and stretch across space. This branch of quantum field theory is called topology, and it reveals that the vacuum is not a single uniform state but a landscape of distinct valleys, each separated by energy barriers that particles can tunnel through. The key players in this story are non-perturbative solutions, objects that cannot be found by the usual method of adding up small corrections. They are like islands that appear only when you look at the whole ocean, not just the waves. The simplest example is an instanton, a localized ripple in a gauge field that exists for an instant in time. An instanton is not a particle you can catch in a detector. It is a tunneling event, a brief fluctuation that connects one vacuum configuration to another with a different topological twist. This tunneling is essential for understanding the structure of the strong nuclear force. In quantum chromodynamics, instantons explain why the strong force does not violate CP symmetry as much as the equations initially suggest. They provide a mechanism for the mass of the eta prime meson and for the breaking of a symmetry called chiral symmetry. Without instantons, our predictions for particle masses would be completely wrong. Another class of topological objects is the magnetic monopole. In grand unified theories, the monopole appears as a stable defect left over from a phase transition in the early universe. Imagine a ball of string where all the threads are combed in a direction that points outward from the center. That pattern cannot be smoothed away. It is a topological knot, and it carries a net magnetic charge. Monopoles are predicted by every simple grand unified theory, and their absence in our cosmic neighborhood tells us something important about the history of the universe. Either the symmetry breaking happened in a way that avoided creating them, or the universe underwent a period of inflation that diluted their density to nearly zero. The search for monopoles continues in cosmic ray detectors and in ancient rocks that might have trapped a passing monopole long ago. So far, none have been found, but every null result refines our understanding of what happened at the highest energies. Topology also plays a crucial role in confinement, the mysterious property that keeps quarks locked inside protons and neutrons. In quantum chromodynamics, the vacuum is filled with a complex tangle of gluon fields that form something like a tube between quarks. As you try to pull two quarks apart, the tube stretches and stores energy. When the tube reaches a certain length, it breaks, producing a new quark and antiquark pair. This process, called string breaking, is a topological effect. It arises because the gluon field cannot be smoothly deformed back to zero. It is knotted in a way that forces confinement. The mathematics of this knotting is described by something called the Wilson loop, a measure of how the field behaves as you go around a closed path. If the Wilson loop follows a particular area law, the theory confines. If it follows a perimeter law, the theory deconfines and quarks can roam free. This area law has been confirmed by lattice QCD simulations. It is a direct manifestation of the deep geometric structure of quantum fields. Beyond confinement, topology explains how chiral symmetry gets broken spontaneously in the strong force. The vacuum is not symmetric under the exchange of left and right-handed quarks. Instantons are responsible for that breaking, and without them, the pion would be far heavier than it is. The pion's lightness is a direct consequence of topology, a whisper from the twisted structure of the vacuum. These topological features are not mathematical curiosities. They are essential to the fabric of reality. They dictate why protons are stable, why quarks cannot escape, and why the universe today contains so much matter and so little antimatter. Each instanton, each monopole, each twist in the fields carries information about the way the cosmos cooled and settled into its present state. They reveal that quantum fields are not just clouds of probability. They are geometric objects woven from patterns that span the entire universe, and their topology holds the key to some of the deepest puzzles in physics. Time flows in only one direction, yet the fundamental equations of physics do not care which way you run the clock. This stubborn fact, the arrow of time, is one of the deepest riddles connected to quantum fields. In the microscopic world described by quantum field theory, every process is time reversal symmetric. If you take a film of two particles colliding and play it backward, the reversed collision is just as valid according to the equations. Nothing in the laws themselves picks out a forward direction, but in the world we experience, time has a clear, irreversible march. Eggs break and do not unbreak. Coffee cools and never warms itself. Memories accumulate forward, never backward. The source of this asymmetry, the reason why the past is different from the future, is not written into the quantum fields themselves. It comes from the initial conditions of the universe and from the way those fields interact with an expanding cosmos. The second law of thermodynamics tells us that entropy, a measure of disorder, always increases. The universe began in an extraordinarily low entropy state, a hot, dense, smooth fireball where every particle was packed uniformly. As it expanded and cooled, structures formed, stars ignited, galaxies assembled, and entropy climbed. The arrow of time follows the rise of entropy. But why did the universe start with such low entropy in the first place? That is a question about the initial condition, and it may be tied to the quantum fields that drove cosmic inflation. During inflation, the inflaton field produced an enormous burst of expansion that ironed out any irregularities, leaving the universe incredibly smooth and homogeneous. That smoothness is the low entropy seed from which all later structure grew. Without that special beginning, the arrow of time would not point the way it does. The expansion of the universe also plays a role through the cosmological horizon. When you look out into deep space, you see a boundary beyond which light has not had time to reach us since the Big Bang. That horizon is a kind of screen, and it interacts with quantum fields in subtle ways. Just as an accelerating observer sees a thermal bath of particles due to the Unruh effect, a horizon in an expanding universe can produce a similar glow. This radiation, sometimes called Gibbons-Hawking radiation, carries entropy and contributes to the overall arrow. The horizon is not a solid wall, but it marks a limit beyond which we cannot see, and that ignorance translates into an increase in entropy over time. Now add the quantum measurement problem to this mix. When a quantum system interacts with a measuring device, the smooth evolution of the wave function seems to collapse into a definite outcome. This collapse is not reversible. It introduces an arrow of its own from many possibilities to a single actuality. Some physicists argue that this collapse is connected to the cosmological horizon, that the universe itself acts as a kind of observer that decoheres quantum states as they pass beyond the horizon. The result is a unified picture where the arrow of time emerges from the interplay between quantum fields, the expansion of space, and the horizon that defines what we can know. But no one has proven this link. The arrow of time remains an open puzzle, a place where our most successful theories meet a boundary they cannot cross. Quantum fields tell us that time reversal is broken not by the equations, but by the stage on which they are played, a stage that began with a single, perfect, low-entropy moment and has been winding down ever since. The question of why that moment existed and whether the arrow will eventually reverse or dissolve is still waiting for a definitive answer. The fields that fill the void may hold the clue, but they are not yet ready to give up their secret. The arrow of time may not be a universal law, but a local accident in a far larger multiverse. This idea emerges directly from the behavior of quantum fields during eternal inflation. In the standard inflationary picture, the inflattened field rolls down its potential, eventually stopping and reheating the universe into a hot Big Bang. But in many models, the field does not stop everywhere at once. Quantum fluctuations cause it to jump upward in some regions, keeping those regions inflating forever while other regions exit and form separate bubble universes. Each bubble is like a vast cosmic pocket expanding at nearly the speed of light, isolated from every other bubble by the relentless stretching of space. Inside each bubble, the inflattened field eventually settles into a minimum of its potential, but that minimum is not the same everywhere. Different minima correspond to different configurations of the quantum fields that fill that bubble. The masses of particles, the strengths of forces, and even the number of spatial dimensions can vary from one bubble to the next. This is the string theory landscape, a vast collection of possible vacuum states, each with its own effective field theory. The number of such vacua is staggering, estimated at 10 to the 500 or more, a number so large that it dwarfs the number of particles in our observable universe. The multiverse is not a single cosmos but a branching tree of bubbles, each with its own physics. This picture raises a profound problem known as the measure problem. If there are infinitely many bubbles and our bubble is just one among them, how do we calculate the probability of observing any particular property? After all, in an infinite multiverse, every possible outcome occurs infinitely many times. Naively, all probabilities become meaningless. Physicists have proposed different ways to cut off the infinities, such as weighting bubbles by their volume or by the number of observers they contain. But no single measure is universally accepted, and the choice affects predictions. This is where anthropic reasoning enters. The anthropic principle states that we can only observe conditions that allow intelligent observers to exist. In a multiverse with countless different vacuum states, most are inhospitable to life. Perhaps the values we measure for the cosmological constant, the Higgs mass, and the strength of dark energy are not fundamental laws but simply the ones compatible with our existence. This explanation is deeply controversial. Some physicists see it as a cop-out, a way to abandon the search for a deeper reason. Others view it as an inevitable consequence of a vast multiverse, a shift from predicting unique laws to understanding why we find ourselves in a pocket that allows life. Quantum fields are the stage for this entire multiverse. Each bubble universe has its own Higgs field, its own strong force, its own set of particles, all determined by the local vacuum. The fields that we study in our laboratories are just one realization among countless possibilities. The multiverse hypothesis, if true, would mean that the ultimate theory of physics does not pick a single set of laws. It describes a landscape of possibilities, and the universe we inhabit is just one bubble among an endless foam. The measure problem remains unsolved, and the debate over anthropic reasoning continues. But the idea that quantum fields can produce a multiverse has reshaped how many physicists think about the cosmos. It forces us to confront the possibility that our universe is not special, that the laws we observe are not inevitable, and that the deepest questions about why things are the way they are may have answers that lie far beyond the horizon of our own bubble. Entanglement is not just a quirk of particles, it is woven into the very fabric of quantum fields. In the ordinary quantum mechanics of a few particles, entanglement connects two distant objects through a mysterious shared state. But in quantum field theory, entanglement is far more pervasive. It is encoded in the algebra of observables, the mathematical structure that defines what can be measured in any given region of space. Each region of spacetime, no matter how small, has its own local algebra of observables, a set of all possible measurements that can be performed within that patch. These algebras are not independent, they are linked by the rules of quantum field theory, and the most startling consequence is a theorem called Unruh and Schlieder. This theorem states that by acting only on a local region with operations confined to that tiny patch, You can create any state whatsoever in the entire universe, provided the original state is the vacuum. Even a minuscule volume of empty space contains enough entanglement with the rest of the cosmos to allow any distant particle or field configuration to be generated from local actions alone. It means that the vacuum is not a simple empty state. It is a vast web of correlations, a network where every point is entangled with every other point, no matter how far apart. This deep entanglement has a measurable signature in the ground state of any quantum field theory. The entropy of entanglement between a region and its complement does not grow with the volume of the region, as one might naively expect. Instead, it grows with the area of the boundary that separates them. This area law is a universal property of the vacuum. It tells us that most of the entanglement is concentrated at the interface, not spread throughout the interior. The closer you look, the more you find that the correlations lie on the surface. This behavior is strikingly similar to the holographic principle, which states that the information content of a volume of space is encoded on its boundary. The area law for entanglement entropy is not just a coincidence. It is the reason why holography works. In the AD/S/CFT correspondence, the entanglement entropy of a region in the boundary quantum field theory is exactly equal to the area of a minimal surface in the higher dimensional gravitational space. The geometry of spacetime itself emerges from the entanglement patterns of the quantum fields. Entanglement is not an optional feature or a strange side effect. It is fundamental. It shapes the very structure of the vacuum, determines how information is stored, and even gives rise to the smooth appearance of spacetime. When we observe a particle in one location, we are seeing only a tiny sliver of a vast, interconnected whole. The rest of the universe, the fields that fill every corner of the cosmos, are entangled with that particle in ways we are only beginning to understand. The more we study these connections, the more we realize that separation is an illusion. Everything is linked through the quantum fields, and entanglement is the thread that binds it all together. Entanglement forces us to confront a deeper puzzle that quantum field theory inherits from ordinary quantum mechanics. This puzzle is called the measurement problem, and it asks a simple but devastating question. What happens when a quantum system interacts with a measuring device? In the usual textbook story, a particle exists in a superposition of many possible states until a measurement occurs, at which point the superposition collapses into a single outcome. But no one has ever described exactly how or when that collapse takes place. The equations of quantum mechanics themselves never include collapse. They only describe how the wave function evolves smoothly in time. Collapse is an extra rule added by hand, a rule that seems to violate the very principles of the theory it is supposed to complete. Quantum field theory inherits this problem in full force. Fields, like particles, exist in superpositions. The vacuum itself is a superposition of infinitely many configurations of virtual particles. When you measure the position of an electron or the strength of an electromagnetic field in a tiny region, you are forcing the field to choose a definite value. But the equations of quantum field theory do not tell you how that choice happens. They only describe the probabilities of each possible outcome. This is not a minor technical inconvenience. It strikes at the heart of what it means to have a fundamental theory. For many decades, physicists thought they could sidestep the issue by appealing to decoherence. Decoherence occurs when a quantum system becomes entangled with its environment. The environment, whether it is air molecules, stray photons, or the walls of the laboratory, carries away information about the system. When that information is lost to the vast number of environmental degrees of freedom, the system appears to settle into a definite state. But decoherence does not actually solve the measurement problem. It only explains why certain outcomes seem classical. It still cannot tell you which specific outcome you will see or why you see only one. the branching of possibilities described by quantum mechanics continues, and the observer becomes entangled with one branch. Some interpretations, like the many worlds interpretation, accept this branching literally. They say that all possible outcomes happen, each in its own separate universe. The observer splits into multiple copies, each experiencing a different result. In this view, there is no collapse at all. The wave function evolves deterministically, and the appearance of a single reality is an illusion created by our subjective experience of only one branch. Quantum field theory fits naturally into the many worlds picture. The quantum fields exist everywhere, and their evolution is unitary, meaning no information is lost. The branching of worlds corresponds to different configurations of the fields in different regions of the multiverse. But the many worlds interpretation comes with its own conceptual challenges. It multiplies realities without any experimental way to tell them apart. It also raises the question of how probabilities work in a universe where everything that can happen does happen. The problem of measurement becomes even more acute when relativistic causality is taken into account. In a relativistic quantum field theory, space-like separated regions cannot influence each other. An event here cannot affect an event there because no signal travels faster than light. Yet a measurement on one part of an entangled field seems to instantly affect the state of a distant part, a situation Einstein called spooky action at a distance. The resolution, according to the standard view, is that the correlations are pre-existing in the entangled state. No signal is transmitted, so causality is not violated. But the measurement event itself still requires a non-local collapse of the wave function if you accept the Copenhagen interpretation. That non-locality clashes with the spirit of relativistic field theory, where interactions are strictly local. This tension has led some physicists to argue that a complete understanding of quantum fields may require solving the measurement problem first. Without a clear account of what happens during a measurement, the theory remains operational rather than fundamental. It tells you how to calculate probabilities, but not what reality is like when no one is looking. The search for a resolution continues. Some pursue objective collapse models where the wave function collapses spontaneously at a certain rate. Others explore pilot wave theories where particles have definite trajectories guided by the quantum field. Still others embrace the many worlds view and argue that the appearance of collapse is a consequence of how we decohere into branches. Quantum field theory does not choose sides. It remains neutral, a mathematical framework that works brilliantly for prediction but remains silent on ontology. The great challenge ahead is to find a description of nature where the act of measurement is not an extra rule, but an emergent consequence of the fields themselves. Until then, the measurement problem stands as a quiet reminder that our most successful theory is also incomplete. The fields that fill the universe obey rules we understand well, except for the very moment when they are observed. And that moment, the moment when possibility becomes actuality, may hold the key to the deepest layer of reality yet. Dark matter is the most persistent ghost in quantum field theory. Every galaxy spins too fast, every cluster of galaxies bends more light than it should, and the cosmic microwave background shows patterns that require extra mass we cannot see. The evidence is overwhelming, but the particle behind it remains hidden. The most natural candidates emerge from extensions of the standard model, from quantum fields that interact so weakly with ordinary matter that they slip through detectors undetected for decades. The leading theory is the weakly interacting massive particle, or WIMP. These particles are heavy, perhaps tens to hundreds of times the mass of a proton, and they interact through the weak nuclear force and gravity alone. They appear naturally in supersymmetric extensions of the standard model, where the lightest supersymmetric particle, often the neutrino, is stable and electrically neutral. The neutrino is a mixture of the photino, the xeno, and the Higgsino, all superpartners of the known gauge and Higgs bosons. In the early universe, these particles would have been produced in thermal equilibrium, then frozen out as the universe expanded and cooled. Their relic density, the amount that remains today, depends on their annihilation cross-section. Remarkably, if you assume a WIMP with a mass around 100 giga-electronvolts and an interaction strength similar to the weak force, you get exactly the right abundance to account for all the dark matter. That coincidence is known as the WIMP miracle, and it drove a massive experimental effort to detect them directly. Underground detectors like xenon and LZ are filled with tons of liquid xenon or argon, waiting for a WIMP to collide with a nucleus and produce a tiny flash of light or a pulse of ionization. So far, no convincing signal has been seen, pushing the possible cross-sections lower and lower. The WIMP window is narrowing but not yet closed. Another class of candidates takes us back to the neutrino sector. Neutrinos are already known, but they come in three types: electron, muon, and tau, all with very small masses. There are hints from experiments that there may be a fourth, heavier neutrino that interacts even more weakly, called the sterile neutrino. Unlike the three active neutrinos, sterile neutrinos do not feel the weak force at all. They only interact through gravity and possibly through mixing with the active neutrinos. In the early universe, sterile neutrinos could be produced through oscillations, and if their mass lies in the kiloelectronvolt range, they could be a warm dark matter candidate, one that moves fast enough to suppress the formation of small-scale structures. This is an active area of research, with X-ray telescopes searching for a faint signal from sterile neutrino decay in galaxy clusters. A decay would produce a monochromatic X-ray line, a fingerprint of the particle. Several claims have been made over the years, but none have been confirmed. The search continues. Both WIMP and sterile neutrinos arise from straightforward extensions of the standard model. Supersymmetry, grand unification, and neutrino mass models all predict new fields that could host the dark matter particle. The fact that we have not yet detected them does not mean they are not there. It means we need larger detectors, more sensitive telescopes, and perhaps even new ways of thinking. Dark matter is not a single particle but a field, a quantum field that fills the universe, fluctuating, interacting only through the tiniest of couplings. It may be that the dark matter is not a WIMP or a sterile neutrino at all, but something even more exotic, like an axion or a fuzzy dark matter scalar field oscillating at a very low frequency. The diversity of theoretical possibilities is staggering, and each one traces back to the same fundamental language of quantum fields. The mystery of dark matter is not just a problem of missing mass. It is a window into a hidden sector of reality, a layer of the universe that coexists with ours but barely interacts. The fields that make up this dark sector may hold the key to understanding galaxy formation, the early universe, and even the ultimate unification of forces. Until we catch their whisper in a detector or their glow across the sky, we will keep building and searching, and when the signal finally comes, it will reveal not just a new particle, but an entirely new branch of the quantum field theory that governs our cosmos. Neutrinos are the lightest known particles, and their tiny masses have puzzled physicists for decades. Unlike every other fermion in the standard model, neutrinos have masses that are at least 1,000,000 times smaller than the electrons. Some theories even suggest they are their own antiparticles, a property called Majorana nature that would rewrite the rules of particle identity. The most elegant explanation for this extreme lightness involves a mechanism that connects them to the very heaviest particles imaginable. This is the seesaw mechanism. The idea is simple yet profound. Add a new heavy neutral field to the quantum field theory, a right-handed neutrino that does not participate in the weak interaction. This right-handed neutrino has a huge mass far beyond the reach of any collider. Because it is heavy, it forces the ordinary left-handed neutrino to become very light through a kind of lever effect. The heavier the right-handed partner, the lighter the ordinary neutrino appears. That is the seesaw. There are three main versions of this mechanism. Type I uses the heavy right-handed neutrino alone, coupling it to the Higgs field and the ordinary neutrino through a Yukawa interaction. The resulting mass matrix has a natural hierarchy. The heavy eigenvalue is enormous, the light one is tiny. Type II replaces the single Higgs field with a new scalar field that carries weak charge. This new field, a complex triplet, generates a small vacuum expectation value that directly gives mass to neutrinos while leaving other particles unaffected. Type III adds a heavy fermion that is a triplet under the weak force instead of a singlet. Each version predicts different signatures in experiments, such as rare nuclear decays or deviations in Higgs-Boson properties. They all share the same core idea. New quantum fields beyond the standard model are required to give neutrinos mass. These heavy fields are not just theoretical curiosities. They may hold the key to one of the greatest cosmic mysteries, the dominance of matter over antimatter in the universe. In the early universe, equal amounts of matter and antimatter should have been created, annihilating each other completely, leaving nothing behind. Yet we exist. Something must have generated a tiny excess of matter. This process is called baryogenesis, and a leading candidate is leptogenesis. In leptogenesis, the heavy right-handed neutrinos from the seesaw mechanism decay in the very early universe. Their decays violate both lepton number and CP symmetry, producing slightly more leptons than antileptons. This net lepton number is then converted into a net baryon number through a hypothetical process called sphalerun, which is active at high temperatures. The result is the matter-dominated universe we observe. The connection is beautiful. The same fields that explain why neutrinos are so light also explain why anything exists at all. The discovery of neutrino oscillations in the late 1990s proved that neutrinos have mass and that new physics must be hiding beyond the standard model. Since then, experiments like CamLand, SuperCamiocand, and others have measured the tiny differences between neutrino masses, but the absolute scale remains unknown. Future experiments, such as those looking for neutrinoless double beta decay, could confirm whether neutrinos are Majorana particles. If neutrinoless double beta decay is observed, it would show that neutrinos are their own antiparticles and directly support the seesaw mechanism. It would also fix the scale of the heavy right-handed neutrinos and point toward the energy of leptogenesis. Neutrino masses are a whisper from a hidden world. They require new fields, new particles, and new symmetries that operate at energies far above what we can produce in laboratories. Yet their effects are written into the fabric of the cosmos, from the rarest nuclear decay to the abundance of matter that fills every star and galaxy. The search for those fields continues underground in particle beams and in the faint light of distant supernova. And when we find them, we will have uncovered a new layer of the quantum field theory that built our universe. Dirac fermions and Majorana particles also emerge inside ordinary crystals. These exotic entities, once thought to belong only to the highest energy physics, appear as low-energy excitations in materials that we can hold in our hand. This is the world of condensed matter analogues, where quantum field theories are not just mathematical abstractions but tangible phenomena that dance through lattices of atoms. In a sheet of graphene, a single layer of carbon atoms arranged in a honeycomb pattern, electrons behave as if they are massless. They follow the same relativistic equation that describes neutrinos and high-energy particles, the Dirac equation. The lattice acts as a stage where the quantum field of the electron becomes a two-dimensional version of a relativistic field, complete with a linear energy-momentum relation. Physicists can manipulate graphene with electric fields and magnetic fields, tuning the Dirac fermions in ways that are impossible with real particles in a vacuum. This allows them to study quantum electrodynamics in a regime where the fine structure constant is effectively larger. revealing phenomena like the Klein paradox, where particles tunnel through barriers with perfect transmission. Topological insulators take this further. These materials are insulating in their interior but conduct electricity on their surfaces with perfect dissipationless channels. The surface electrons are protected by the topology of the material's band structure. They are described by a quantum field theory that includes helical Dirac fermions, where the direction of motion is tied to the electron's spin. These edge states are incredibly robust, resistant to impurities and defects because they are topologically protected. This is a direct manifestation of the same topological ideas that explain instantons and confinement in the strong force. In the laboratory, topological insulators allow researchers to create and study analogues of the quantum spin Hall effect and even Majorana zero modes. Majorana modes are particles that are their own antiparticles, predicted in neutrino physics and supersymmetry. In condensed matter, they appear as bound states at the ends of certain superconducting nanowires or at the edges of topological superconductors. These Majorana modes could be used for topological quantum computing, where information is stored in a way that is inherently protected from decoherence. In superfluid helium-3, a quantum liquid that flows without viscosity, the order parameter itself is a complex field with multiple components. This system hosts a Higgs mode, a massive amplitude fluctuation of the order parameter that is strikingly similar to the Higgs boson of particle physics. When researchers cool helium-3 to near absolute zero and apply pressure, they can watch the Higgs mode appear as a collective oscillation of the entire fluid. It is a direct analog of the mechanism that gives mass to elementary particles, studied in a controlled, accessible environment. The Higgs mode in superconductors is another example, seen as a fluctuation of the superconducting order parameter that couples to light. There is also the analog of Hawking radiation in fluids. By creating a flowing stream of water or ultra-cold atoms that exceeds the speed of sound, physicists can form an acoustic black hole, a sonic horizon from which sound waves cannot escape. Quantum fluctuations at that horizon produce a thermal glow of phonons, exactly analogous to the Hawking radiation predicted for gravitational black holes. This experiment has been performed with Bose-Einstein condensates and with water, and the results match theoretical predictions. These analog systems are not toys. They are powerful tools for quantum simulation, where a complex quantum field theory that is difficult to compute on a classical computer can be mapped onto a controllable condensed matter system. For example, the Hubbard model of strongly correlated electrons can be realized with ultra-cold atoms in optical lattices, allowing physicists to study high-temperature superconductivity and the phase diagram of quantum chromodynamics in a simplified setting. The hope is that these experiments will reveal new phenomena and provide insights into the fundamental theories of particle physics and cosmology. The quantum fields that fill the universe may be distant and elusive, but their echoes appear in the humble materials of the solid state. By studying these echoes, we are learning to simulate the Big Bang, to reconstruct the birth of particles, and to uncover the hidden structures that govern reality at every scale. The boundary between fundamental physics and condensed matter is dissolving, and with it, our understanding of what is truly fundamental is being reshaped. This reshaping reaches all the way to the nature of time itself. For centuries, time was treated as a stage, a universal backdrop against which events unfold. But quantum field theory suggests something far stranger. Time may not be fundamental at all. It may emerge from the statistical properties of the quantum fields that fill the universe. This idea is called the thermal time hypothesis, and it was developed by the mathematicians Elaine Connes and Carlo Rovelli. They asked a simple question. What if time is not an independent dimension, but a consequence of how a quantum system mixes its states? The key lies in a deep mathematical structure called a von Neumann algebra. Every quantum field theory can be described by such an algebra, a vast collection of observables that defines what can be measured in any region of spacetime. The algebra itself contains a special operation called modular flow. Without getting lost in the mathematics, modular flow is a natural, built-in evolution that arises from the way the quantum states are entangled. It provides a direction, a sense of ordering, a temperature. In fact, for any given state, the modular flow defines a physical time, one that depends on the state itself. This is a radical departure from the usual picture. Instead of time being a fixed coordinate, it becomes a derived quantity, intimately tied to the quantum fields and their entanglement. The connection to the Unruh effect becomes clear. An accelerating observer experiences a thermal bath of particles because the modular flow of the vacuum state, as seen from their perspective, has a non-zero temperature. The time they feel, the flow of their own proper time, is exactly the modular flow associated with their accelerated trajectory. In a sense, time and temperature are two sides of the same coin. Both emerge from the statistical structure of the quantum fields. If this hypothesis is correct, then time in quantum gravity must be understood in a completely new way. General relativity treats time as a dynamic geometric entity, while quantum field theory treats it as a parameter. The thermal time hypothesis bridges this gap by saying that time is neither a fixed background nor a mere parameter, but an emergent property of the quantum fields themselves. In the deep quantum gravity regime, where spacetime itself is fluctuating, there may be no pre-existing time at all. Instead, the flow of moments arises from the modular flow of the fundamental algebraic structure. This idea redefines the role of fields in temporal dynamics. Fields are not just the source of particles and forces. They are the very fabric that generates the arrow of time, the rhythm of change, the passage from one instant to the next. The thermal time hypothesis remains a frontier of theoretical physics, untested by experiment but deeply compelling. It suggests that the most familiar aspect of our experience, the steady march of time, is not a given. It is a consequence of the quantum fields that weave the universe together, a statistical shadow cast by the entanglement of everything with everything else. The 30 theories we have explored reveal a universe far richer than any single story could capture. From the steady hum of the Higgs field to the restless sea of virtual particles, from the twisted topology of instantons to the holographic promise of entanglement, each idea adds a new layer to our understanding of reality. Quantum field theory is not just a tool for calculating particle collisions. It is the language in which the cosmos writes its own history. Every force, every particle, every moment of change emerges from fields that fill every corner of space. These fields are the invisible threads stitching together the smallest quark and the largest galaxy, the first instant of inflation and the slow evaporation of a black hole. Yet many of the theories we have discussed remain provisional. The inflation has never been directly detected. The axion, if it exists, still hides from our most sensitive experiments. Supersymmetry, once the brightest hope for unification, grows more elusive with each passing year. The multiverse, the big bounce, and the emergence of time itself from quantum entanglement are bold visions, but they rest on mathematical beauty rather than experimental proof. This is not a weakness of the field, it is its greatest strength. Quantum field theory gives us a framework to ask precise questions about what we do not know, to design experiments that push the boundaries of detection, and to imagine realities far beyond our own. It teaches us that the vacuum is not empty, that acceleration creates warmth from nothing, and that information may never truly be lost. The quest for a unified understanding continues, driven by the same curiosity that led us to discover the Higgs boson and to map the faint afterglow of the Big Bang. The next breakthrough may come from a new collider, a deeper underground detector, or a flash of insight in a quiet office late at night. Every viewer of this journey now shares in that quest. Which of these theories resonates most with you? Perhaps the strange observer-dependent warmth of the Unruh effect, or the elegant simplicity of the seesaw mechanism, or the radical idea that spacetime itself is a hologram. Let us know in the comments below. The conversation does not end here. If you want to continue exploring the deepest questions in physics, subscribe and stay tuned for more journeys into the unknown. The fields are always there, waiting to reveal their next secret.